But we have a pretty good idea of where we're going there. Okay. How many patients stayed for less than 9 days? Well, it's this group of patients here: 1, 3, and 2. So 7 patients. What's the probability of staying in the center for 7, 8, 9, or 10 days? Would be 7. Would be 1 person. 4 persons added to that would be 5 persons. Okay, and 1 person would be 6 persons. So 6 out of the 20 people would be 15% of them stayed for that period of time. And of course, the median, we know there's 20 people there, so we counted up. The 10th person was in the ninth bar going up, and in the ninth bar coming down. It worked both ways. But you're absolutely right. It is 9, not 7. Okay, so let's take a look at the next one. Okay, so now probability. There are 2 events rated to Mexican American children born in Arizona in 1986. Event A, the child's gestational age is less than 37 weeks. Event B, the child's birth weight is less than 2,500 pounds. Okay, in other words, we're looking at premature births. 6 out of 20 is 30%. Yes, not 15%. You're absolutely right. I'm so glad I put that chat window up so you guys could keep correcting me. That's right. 6 out of 20 is 30%. Um, 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 let's see, where was it? Okay, the probability of event A, probability of of a birth being at less than 37 weeks is 0.14, 14%. The probability of event B, the child weighing less than 2,500 grams, is 0.5. The probability that both occur, the child is less than 37, born less than 37 weeks, and that the child is less than 2,500 pounds 2,500 grams at the same time, probability that they occur simultaneously is 0.03. Are A and B independent? Okay, I'll ask you guys that. Are A and B independent events? Well, you're public health people, right? Does premature birth and low birth weight, does that seem like they're independent? No, they're dependent, right? Now, how do we know from the math that they are dependent and that they are not independent? Anybody want to hazard a guess at that? I'm going to give you a hint. Okay. Remember when we were talking about probabilities of 2 independent events occurring together? For instance, let's say I told you the probability of people in a population being insured is 70%. Okay. And we pick 2 individuals at random. Okay. 2 independent events. We pick one, then we pick the other, both at random. Okay. What's the probability that both are insured? Well, we would multiply probability of one times the probability of the other. In other words, zero point 0.7 times zero point 0.7. If they're independent events, we just multiply it out, and the probability of both being insured would be 0.49. Okay, let's take a look at this. The probability of event A is 0.14. The probability of event B is 0.50. If we multiply 0.14 times 0.50, we get 0.07. In other words, the probability, if they are independent, then the probability of their occurring together is about 7% or 0.07. Well, as it happens, we found that in real life, the probability that they occur simultaneously is 0.03. Well, since it isn't 0.14 times 0.50, that's an indication to us that these are not independent events. Okay, well, I would actually tell you the truth if this were real data. Well, this probably would have been higher than the 0.07, higher than the probability that they were independent events, since they both would occur, are not unlikely to occur together, right? But just the fact that we can multiply 0.14 times 0.50 and not get the result that we expected tells us that they are not independent events. Okay, kind of a little bit of a tricky question, right? But you get what we're driving at here and why we asked that question. If they were independent events, we could just multiply the 2 of them together. Okay, what's the probability that, let's assume for a second they are independent events. Okay, what's the probability? The probability that they would occur together is 0.14 and 0.50. Okay, what's the probability that the gestational age would be more than 37 weeks, but the child's birth weight would be less than 2,500 grams? Anyone want to hazard a guess there? Probability that the Uh, Gestational age is more than 37 weeks, assuming, different problem now, assuming that these are independent events, probability that the child's gestational age is more than 37 weeks and the child, randomly selected child, weigh less than 2,500 grams. What would you say that probability is? How would you figure that out? Okay, let's think about that. Probability that the child's gestational age is less than 37 weeks, event A, is 0.14. Probability that it's more than 37 weeks is 0.86, right? And the probability of event B, which we're keeping the same, is 0.50. So the probability of them occurring together would be 0.86 times 0.50 if they were really independent events. Okay, but they're not. So, this is just an example of what other kind of question you might get on here. How did they? It's made up example. The point here is, Christina. The point here is that if these were independent events, then you would expect the probability that they occur simultaneously is 0.14 times 0.50. Had this been a better, had this been a better thought out problem, we probably should have made this maybe 0.20 or something like that, something that's more probable than them not being associated, since you would usually associate these two things together. Okay, but you get the point, right? Okay. We do have something on variables. Okay. Identify each type of variable below. The size of a transplanted organ. Okay, for instance, a liver. I guess that would be in grams, right? Anybody want to? What is that? Nominal, numerical, discrete? Okay, I guess we all know that's going to be numerical, right? It's going to be a not discrete numerical. It's going to be continuous numerical. The number of calls to a drug abuse hotline in a specified month. Okay, that's going to be numerical also, but it's going to be discrete numerical, right? It's going to be a whole number. Okay, you're not going to get half a call. The length of time that a cancer patient survives after diagnosis. I would say that's probably going to be numerical. It's probably going to be continuous. Okay, even though you might look at it, it could go either way. You could say numerical, discrete, because most likely that would be reported in days or months or some specific unit of time. So it's probably going to be a whole number, but it's certainly going to be numerical. The types of surgeries performed in a specific hospital? Okay, that's going to be nominal, right? It's going to be names of the surgeries. And I'm going to add one to those, the outcomes from a surgery, good, fair, poor, good, fair, or poor. Okay, and so that would be, of course, we wouldn't call it ranked. It is ranked, but we would use the term ordinal. Okay, ranked is, yeah, kind of right, but not really. There is a special form of data and a special analysis. I don't know if we get to that in this semester or not, but there is a special kind of analysis that you can do on ranked data. In other words, let's say that you had 20 people in a class and they took a test, and each one of them got a score on the test. One person got a 99, one person got 89, another person got 65, another 78, and so on and so forth. You could, instead of looking at these specific scores, you could just look at the data as what was that person's rank? Was he first, second, third, fourth, fifth, and so on and so forth? Almost like a race. Okay, and analyze the data differently than you would with the specific numerical results. So ranked data is a special form of data. We would normally call good, fair, poor, the pain scale, what level of pain you were at, scale of 1 to 10. We would call that ordinal data for the most part, okay, rather than ranked data, because we're going to reserve the term ranked for something later on. Okay, now I'm going to go over the normal distribution. I don't think we're going to do anything on Chebyshev, but it's Chebyshev's pretty straightforward. But normal distribution, we're going to bump heads with for quite a while. Okay, now this problem says, suppose student weights are normally distributed with a mean of 150 pounds and a standard deviation of 20 pounds. Okay, this picture is roughly what the distribution might look like. Okay, what's the probability of weighing more than 170 pounds? Okay, hang on just 1 second here. Okay, I'm gonna pull up a notepad here, and I'm gonna just sketch something quickly here. Okay, here's our normal distribution. Our mean is 150 pounds. Our standard deviation is equal to 20, I believe. And we're looking at what's the probability of weighing more, a randomly selected individual weighing more than 170 pounds. Okay, well, we know that the empirical formula tells us that we would expect 68% of our population to be within one standard deviation below and one standard deviation above the mean. Okay, means 150 in this case. Standard deviation at 20, so we're saying that we would expect 68% of the people in this population to be between 130 and 170. Okay, so what's the probability that we would expect that we would pick an individual and they would weigh more than 170 pounds? Well, we got 68% of the population here between these 2 points, right? So that means we have 32% of the population unaccounted for. Since this distribution, normal distribution, is symmetrical, that means that half of that, 16%, is going to be below one standard deviation below the mean, and 16% is going to be above one standard deviation above the mean. So the question asks us what percentage, or what's the probability of randomly selecting a person that weighs more than 170 pounds in this population. Probability of doing that is 16%. Okay, using this empirical formula. Okay, so, or empirical rule. What's the probability of weighing more than 190 pounds? Okay, and I like sketching this out because it's a lot harder to make a mistake if you sketch it out. So 190 pounds, right, is 2 standard deviations above the mean. 2 times 20 is 40. 150 plus 40 is 190. So we're 2 standard deviations above the mean. So that would represent 95% of the population of this distribution. Okay, 95% of this distribution would leave 5%, 2.5% at the bottom, and 2.5% at the top. Okay, so what's the probability of weighing more than 190 pounds if you randomly select in this population? Well, it's going to be 2.5%, or 0.025. Okay, now remember, the empirical rule is an estimate. Okay, we're going to find out that 2 standard deviations above the mean leaves a tail that's a little bit different than 2.5%. But we'll see that later on as we move on. Okay, okay. Now, we could ask you some more complicated questions than this. For instance, what if I asked you what's the probability of weighing between 130 and 190 pounds, right? Weighing, let's say, that our randomly selected individual weighs more than 130 pounds but less than 190 pounds. What's the probability of that occurring? Okay, let's take a look at this. Probability of weighing more than 130 pounds, well, let's see. That's going to include everything from this point to the right, and weighing less than 190 pounds is going to be, oops, I should put this way. Let's see, y is less than 190 pounds, and y is greater than 130 pounds. Should put my arrows that way, my carrots that way. So less than 190 pounds is going to be everything from this side back. Okay, so we want to find the area from 1 standard deviation below the mean to 2 standard deviations above the mean. Okay, so one of the ways we can do this is, given what we already know about this, we know that below 130 pounds represents 16% of the population, and above 190 pounds represents 2.5% of the population. So we're excluding from this range, we're excluding 16 plus 2.5, or 18.5%, or 0.185 of that population. So we can say, well, we want to know the area between these two. Well, it's going to be just 1 minus 0.185, or 81.5% of the population. Okay, that sound right? I think that's right, right? Okay. Let's see. Yes, I think that's right. Okay, so another way for us to do this would be to add up these different blocks. Start with the mean, and I know between one standard deviation, the mean, and one standard deviation below is 32%. Okay, from one standard deviation to 170 is another 32%. Oh, excuse me, 34% and 34%. Okay, and from or if I want to go from the mean to 90%, right, to 190, or the point where we are for two standard deviations above, from there to that point is 47.5%. So we can add 47.5% for the portion above the mean to 34% for the portion that's below the mean, and add up. We should add up with the same amount. Okay. Are you guys comfortable with that, or should I resketch that on a piece of paper where, on another note where it's easier to read? Everybody okay with that? Okay, got it. Anybody want me to resketch that on a new note? Okay, good. I think you guys are okay with this, right? Okay, so now that's great for situations where it's an even number, or an integer number of standard deviations above or below the mean, and where an estimate is acceptable. Okay, but there are going to be times when we need to get a little bit more accurate result, and also when we need to work with numbers that are not exactly a certain number of standard deviations. So let's take a look at this problem. For 5,459 pregnant women using this hospital in Denmark in a 2-year period, reported unelected gestation until birth, the mean was 281.9 days with a standard deviation of 11.4 days. Let me put that on here right away. 281.9. Oops. Okay, our mean is 281.9. Our standard deviation is 11.4. Okay, 11.4. If the gestational times are normally distributed, what is the approximate proportion of babies that will not be born prematurely? Okay, and we're defining the prematurely as 258 days or less. Okay, so what's the probability, given that these are normally distributed, what's the probability that a baby given this distribution, will be born at less than 258 days? Okay, so 258 days is going to be over here somewhere. So we want to know, what is the area of this portion of the normal distribution? What percentage of this entire distribution is this? What percentage of the births does that represent? Okay, so we need to know, what's the z-score here? Okay, well, z-score, we can calculate z-score by counting the number of standard deviations down from the mean. 11.4 would be 281 to 258. Looks like it's going to be like 2 or 3 standard deviations below the mean. Exactly how many standard deviations? Well, we can do that by just saying z is equal to the value that we're interested in minus the mean over the standard deviation. It's going to be obvious like this is just a way of counting z-scores. Okay, in other words, it's 258 minus 281.9 over 11.4. Okay, that's going to be equal to, and I'm going to take my calculator out. Okay, let's get the calculator, and 258 minus 281.9 equals minus 23.9. Divide that by 11.4, and the number of standard deviations is minus 2.0, and I'm going to round it to 2.1. I'm going to round it to minus 2.1. Okay, I'd leave an extra decimal place there if I were you guys. Well, actually, it's actually pretty close to 2.10 if I round it to two decimal places, right? As if I recall it correctly. Okay, so that's how many standard deviations below the mean that we are. Okay, now had this been just two standard deviations below the mean, we'd have a pretty good guess. In fact, maybe at this stage we should say to ourselves, well, if we were two standard deviations below the mean, we would expect this area to be about 2.5%. So this is a little bit further than 2.2 standard deviations below the mean. So we'd expect a little less than 2.5%, maybe 2.5. Right now, we're going to estimate using empirical rule. Oh, we're looking at about 2% of the births are premature or below 258 gestational days. Okay, so I'm going to keep that in mind because when I actually look up on my Z table what area of the normal distribution this represents, I want to keep that in mind. Okay, so now we're going to need a Z table. Okay, and I'm going to pull that up. And I got one in the background here somewhere. You can look at the one in your book if you want. I'm going to try and use the same one as in your book. Okay, someone says they lost my sound. You guys still hear me? Okay, I think that's just them. They should come. It should bounce back. Sometimes we're on the internet, so sometimes you get a little bit of hesitation in your internet connection, and something might freeze for a moment or two. Don't panic. Usually, this is a pretty stable system. GoToMeeting, so usually it comes back. It's pretty reliable, and it comes back. Let me just pull this up so we can see it. Okay, and if I look in here, let's see where I have it hidden away here, and this is Agresti. Okay, here's ours. Okay, oops, I didn't get the right one. Let me get rid of that. I'm going to get this out of the way too. I didn't get the right one. Let me do that again. Let's see, standard normal distribution. Adjustment. I know I got it here somewhere. Here we go. Up, that's ours. Okay, so let's take a look at this. I'm going to look up the z-score for 2.10. 2.10. Okay, what's the z-score for 2.10? Well, if I use this table, the z-score for 2.10 is going to be, say, z-score of 0.5, 0.1.0, 1.5, 2.0, right? 2.1 would be this line. 2.10 is 0.018 or 1.8%, right? So if I go across, 2.11 would have been 17, 1.7, 2.15 would have been 16, 1.6%, and so on and so forth. Okay, so for 2.10, I'm looking at 2.1 for the first two digits, and the column I'm looking for my third digit is 0 is 0.018. Okay, so this area, remember now that was a positive z-score, wasn't it? Okay, so my z-score, my table, if you look at the top here where it says under table A3, areas in the upper tail of the standard normal distribution. In other words, what it told me is if you have a z-score or a number of standard deviations of 2.1, the area in the upper tail is 1.8%. Right? Well, now I know that my standard normal distribution is symmetrical. So if a z-score of 2.1 gives me 1.8% in the upper tail, a z-score of negative 2.1 gives me an area of 1.8% in the lower tail also. Okay, you guys comfortable with that? See how that worked? This can be done. I'll show it to you using Excel also. Yes, you can do it in Excel also. So this is 1.8%. Remember, I estimated that it was going to be somewhere around 2%. So by using the empirical rule to kind of like help me out and help me make an estimate, I can avoid some mistakes, like thinking that, oh, maybe it's this part of the curve, and it's really like, oh, 50 to here would be 48.2% or something like that. Okay, sometimes not. This one's pretty obvious, but on occasion, you may find that the empirical rule will help you out in making judgments and stuff like that. Okay, let's do this with the, let me show you another curve, man, before I go any further. Not everybody's curve looks like that. This curve is from another textbook. And let me see, this is from Agresti, a different textbook. This one shows you the area of the curve from the z-score to the left. It shows you the lower tail. Not only that, but it also shows you positive and negative numbers. Notice that everything from 0, everything from the second table is above the mean. Positive z-scores are all above 50% of the area, right? Because they include a z-score of 0 is the mean. So if you look into the area to the left of it, it's always going to be 50%. So all of these are areas from that point down. So you can actually look up a negative z-score and look, it's 0.0179. If you round that off, that's 1.8%. Okay, we get a little bit of a different number in here for one reason or another, but 0.018, 0.0179 or 1.79 or 1.8% of the distribution is below that z-score. Now, you could also do it with Excel, as I mentioned. Let me pull that up right now. I hope we weren't asking that for too long because it was a little bit before I actually looked there. Okay, our function that we want is norm dist, parentheses. Now, as soon as that comes up, it gives us an opportunity to put in the value we're interested in, which was 239, I forget, was 258, comma, the mean, which was 281.9, 281.9, comma, and the mean and the standard deviation, which was, how quickly I forget, 11.4. And cumulative, which is always going to be true. Remember, we mentioned that in class. It's always going to be true because false would only indicate like an infinitely small sliver of height. Wouldn't really have a true area. Okay, and we get 1.8% is the area to the left of that value. See, it actually works out. Actually, our table appears to be closer than the other table, or agree better with Excel than the Agresti table. Now, I think you can also use something called norm sdist. Let's see if that function works. Nope. Norm.dist, parentheses, no. Oh, I'm sorry, I didn't put an equal sign. Norm sdist, parentheses. Okay, now norm sdist only asks you to put in the z-score. Up here, we put in both for norm dist, we put in the value, and it calculated the z-score for you. If you know the z-score already, instead of using norm dist, you can use norm sdist, or normal standard distribution. And there, you only have to put in the z-score. So since we know the z-score is 2.1, or excuse me, negative 2.1, I'll just put that in. And we get the value that we got before. Actually, the difference is, I guess, maybe the way I rounded the calculation for the z-score. Okay, so we could use norm dist or norm sdist. Incidentally, there is another one might come in handy, and that's norm inverse, parentheses. And in that one, we put in the probability. In this case, it's 0.018, comma, the mean, which was what was it again? Let's see, 281.9, comma, the standard deviation, which was 11.4, and that will return the value that gives us that z-score, or 258. In other words, if we ask you to tell us give us the value for number of gestational days for less than 3.5% of the children, you could just put in 3% instead of that 0.018. It'll tell you what the value number of days is that would represent 3% of the children being below that value. Okay, so you got a few. I'll just write those here. Norm dist, you have norm sdist, and you have norm inverse. And remember, whenever you do this, when you put an equal sign, put in parentheses, as soon as you put it in the parentheses, it gives you a prompt for how to fill it in. You also have the option of pulling up the function and looking up some help on that function, the part that it gives you here, or you can also click on this and get more help on it. Looks a little bit different. This particular table, the function table, looks a little bit different in Excel than it does in Macintosh, but it's functionally the same. Okay, that okay, guys? Does that make sense? You okay with that? Okay, good. All right, let's move on. And just keep in mind is in case you get no, the answer is 2.5. The answer is 1.8%, right? Because what was the question again? Let me just reiterate what the question was. The question was, what's baby is classified as premature as less than 258 days. If the gestational times are normally, what is the approximate proportion of babies? Oh, I'm sorry. You're absolutely right. The answer is 98.2%. You guys keep catching me in errors here. Okay, you're exactly right. The question asks, what's the probability that the baby will not be born prematurely? I even last time I went over this with somebody, I even underlined the will not be premature. Okay, the probability that they'll be born prematurely was 1.8%. Probability to not be born prematurely is 98.2%. Right, exactly right. Keep reading the questions. It'll help you out on the test. Trust me. Okay. Okay, so let's talk about diagnostic tests. Okay, as a next major subject. Let's see. You have a sample of 100,000 subjects, or population of 100,000 people. Following table classifies whether a subject is HIV positive by whether a screening test, diagnostic screening test for HIV status is positive. Okay, so let's take a look at this. Out of those 100,000 people that took part in this study or that was accumulated in the data on this test, following this screening test, they went through, the whatever the gold standard test is for HIV status that's used nowadays. They went on, and then we compared the results of the screening test that we have here to their actual HIV status, whether they actually have the infection or not. Okay, so we found on the diagnostic test that there were, out of that 100,000 people, there were 500 people who who had HIV, who were positive. There were the remainder 100,000 people, 990,500 were negative, were not HIV positive. Okay, the test correctly identified the people who had HIV 475 out of 500 times. In other words, 500 people had HIV. It correctly identified with a positive test 475 of them. So those are your true positives. Okay. On the other hand, 25 people out of the 500 who had HIV were diagnosed as negative. So these are false negatives. Okay, they tested negative, but they do have the disease. They're in this column, they do have the disease. On the other hand, the number of people that don't have the disease is 100,000 less 500. Okay, that's the number of people here. And we found that out of that total number of people, 94,525 people tested negative. In fact, this would be then true negatives. People in this column don't have the disease, and this is the number of them that tested negative. They're true negatives. Unfortunately, almost 5,000 people out of this almost 100,000 people tested positive, even though their HIV status was negative, even though they really didn't have the disease. Those are false positives. Okay, so we have a test here that catches people that have the disease pretty reliably, and it also predicts pretty reliably people that don't have the disease. I mean, for the most part, 95% of the time, roughly, it was correct. Well, in fact, we're going to determine that. What's the prevalence of HIV status in this particular population? What's the prevalence here? Anyone want to hazard a guess? I'm going to pull up my calculator. Okay, I'm going to do it myself. You guys can do it also. Okay, let's see. We got 100,000 people. We got 500 people who have it, divided by 100,000 people in the population. Okay, I get 0.5%. Did I get that wrong? Again? Don't tell me I got it wrong again, right? No, I think I got it right, didn't I? I see one answer here. Somebody gave me. Okay, I got 0.5%, right? It's 0.5. It's 1/2 of 1%. Thank you. I was starting to doubt myself there. Okay, okay, so it's 1/2 of 1%, right? It's 500 people are HIV positive, 475 and 25. These tested correctly, these tested incorrectly, but these are everybody that's in this column has the disease. You know what I'm gonna do? I'm gonna see if I can't copy this out of here. Let me go to Excel. See if I can get lucky here. Oops, why is it not letting me do that? Okay, I'm gonna scroll up here, see if I can't paste these in here. Oops, nope, I didn't copy it, I guess. Control C. Control up. No, it won't let me copy it in. Let me try a new sheet. Nope. Something happened here. Something's buggy. Oh. Oh, let me quit Excel and reopen it. I guess I'm gonna have to force quit it. And let me reopen it. Okay, I'll cancel this. Let me blow this up a little bit. See if it'll let me do it now. There we go. Okay, this is HIV. This is disease positive. This is disease negative. This is test positive. And this is test negative. Okay, and if I were to lay this out over here, these would be true positives. These would be false negatives, right? Because everybody in the column has the disease. So if they test negative, it's a wrong test. These are true negatives, and these are false positives. Because if they tested positive and they're in this column, they don't have the disease. That's an incorrect test. Okay, so we got 500 people here. Okay, and we have 99,500 people over here for a total of 100,000 people. So the prevalence is the number of people that have the disease over the total number of people in a sample or population, okay, which is 1/2 of 1%, 0.05. Okay, next question. What's the next question they asked us? Next question is find the sensitivity and specificity of this diagnostic test. They asked us to make a judgment, is it a good test? Okay, let's find out what the sensitivity is. Okay, what's sensitivity? Okay, sensitivity is the probability that it will correctly identify people that have the disease. In other words, how out of 500 people who have the disease, how many did it correctly identify as testing positive? So it's going to be equal to 475 out of the 500 people who have the disease. In other words, the sensitivity is 95%. If we tested 1,000 people who we know have the disease, 950 of them will be correctly identified, 50 will be incorrectly diagnosed as negative. Okay, so it's 95% accurate at doing that. The sensitivity is the same idea, except the sensitivity is how well we can identify people that don't have the disease. 99,000, I'm going to put it this way, equals something over something. Well, 99,500 people don't have the disease. In this case, how many people did it correctly identify didn't have the disease? 94,525 out of that 99,000. The sensitivity of the test is 95% accurate also. Okay, so we're pretty encouraged, right? 95% accurate at identifying people that don't, and identifying accurate at identifying people that do. Well, let's take a look at how many positive tests we got altogether. The sum of positive tests, the total number of positive tests out of 100,000 people, was 5,450 people. Total number of negative tests is equal to the sum of the false negatives and the true negatives. Okay, so there are our test results there, right? So now let's see what this tells us now. 500 people have the disease. How many people tested positive? 5,000. Gee, something's wrong there, isn't it? Okay, it seems like we get a lot of positive results. We need another way of measuring how likely it is that if you get a positive result, what does that actually mean? Does it mean you're likely to have the disease for sure? So let's take the positive predictive value. It's going to be equal to the likelihood you really have the disease given that you've tested positive. Okay, so let's see. That's going to be 475 people have the disease that tested positive out of a total of 5,450 people who tested positive altogether. So if you're one of these 5,450 people, the chances that you actually are HIV positive is only about 8.7%, right? So 92% of these people, a little bit more than 92% of these people that tested positive don't have the disease. Well, what does that tell you about the disease? That tells you that you got a problem, because if you're going to get all these false positives, you're going to, forcing people maybe onto drug regimens that could be dangerous. You're going to be, it's going to be traumatizing. It's going to have all sorts of problems and stuff like that. Now, we can also measure something called a negative predictive value, and it's really the same idea. It's equal to, let's see, it's going to be equal to the number of people that really are negative divided by the number of people that tested negative. Okay, and that is 99.97%. In other words, if you're in this group of 94,550 people out of 100,000 that tested negative, well, there's very few people that have the disease in that group. So you're almost certainly negative if you tested negative, unlike if you tested positive. This is the negative predictive value. This is the positive predictive value. One of the things you should keep in mind is that both negative predictive value and positive predictive value, they are forms of what are called conditional probabilities. In other words, what's the probability that you have the disease, right? That you're in this column. What's the probability that you have the disease given that you've tested positive? Well, the probability you have the disease given that you tested positive is 0.08. Similarly, what's the probability that you have the disease if you test negative? If you first test negative, what's the probability that you actually have the disease? Okay, so a conditional probability again. Okay, we're going to take another look at conditional probability and maybe another look at a problem like this, hopefully before we're done. But I think this is a pretty good start. Anybody have any questions about this, about how you would use this? Right, you guys pretty comfortable with diagnostic tests? Okay, guys, okay? Okay, good. All right, now, okay, so we're done with this particular. Are we done with this group? No, we're not. We got one more exercise, computer exercise. Okay, so now at this point, this is something you could use R or SPSS for. For my purposes here, I'm going to use SPSS right now, but you can use R if you want to. Okay, or in some cases, you may be able to use Excel to do most of these calculations. Going to be some of the stuff, especially say the graphics, might be a little bit more cumbersome if you try to do them in Excel. But I'm going to use SPSS. It's available in all the computers in the labs. But if you feel comfortable with R, there's no reason why you can't use R instead. So I'm going to open up something called the Georgia Student Survey. which I have saved on here. We used it a couple of times already for a couple of things, I think. Georgia Student Survey. Well, I have an Excel version of it right here. Here's the Excel version. Just I'll take this excuse to show you something else. Each one of these lines, first line represents the name of a variable. Height, gender, ones and zeros represent male and females. A type of haircut, I guess. Number of days since a haircut, maybe that's what it is, number of days since a haircut. Whether or not they're working, study time, cigarette smoking, so on and so forth. All these, for instance, study time might represent the number of hours per week that they study, or hours per day. Well, at 10 hours, I guess that's not per day. Okay, whether or not they smoke, if they're dating, high school grade point average, college grade point average, so on and so forth. Um, Normally with this, you'd have a code book. It would tell you, the code book would just be simply really a list. It would tell you, for instance, that haircut represents number of days since their last haircut. Gender represents one for, say, male, zero for female, and so on and so forth. And HS, just so you knew, HSGPA represent high school grade point average, college grade point average, CGPA, and so on and so forth. So you'd have a code book that would explain all this so that you wouldn't have any errors. Okay, so, and for instance, for dated, which one represents dating? Uh, 0 or 1. Oh, dated, I guess how many people they dated. I guess that's a numerical variable, and not that they're dating or not. But like I said, that would be summarized. Uh, okay, and some of the other variables as well, especially numerical, the nominal variables like gender and stuff like that. You need the code book to tell you what the numbers summarize. Okay, so now I can work with it. For instance, if I want to know what the for the college grade point averages, what the means and so on and so forth are, I could do this in Excel with some difficulty because there's a lot of students here, or I could import this into SPSS. Now I'm going to save this, save as, and I'm going to save it on the desktop. And I'm going to save it two ways. I'm going to save it first as an Excel worksheet. Then I'm going to save it again, save as. And this time I'm going to tell it I want to save it under the same name, except I'm going to change the format to comma separated values, .csv. And I'm going to say save. I now have it's warning me that I may lose some formatting and stuff like that if I use CSV, because CSV is just text with commas between each field. Okay, but that's okay. I don't mind losing some format. Um, I have two versions of this on my desktop now, the Excel version and that CSV file. That CSV file now is you're able to import that into R, and all these variables will be in R. Now, just another hint is if you're only going to be worried about the gender and the grade point average, you could delete these other values, right? So that you're only left with the variables that you really need. Okay. I might not want to do that myself, but I might want to leave them all together and stuff like that. And I could save that, save that under another name so I don't lose the original file. But just to make things simple, if you know that you're only going to use a couple of those variables, and you want to trim it down just to make things a little easier for you when you open an SPSS or R, you might want to consider that. Okay, so now I'm going to open SPSS. Actually, I'm going to SPSS. Where is it? Where is it? There's R. There we go.